So good morning, everyone. I am Fariha from University of Massachusetts Amherst, and this work is done by me and my advisor, Professor Alexandra Milu. So today I'm going to talk to you about a system that lets you query relational databases without writing any SQL. So we live in a time where the data is highly available. All sorts of people want to use this data. However, the problem is people who don't have expertise in data don't have a simple way to use it. And about 65% of the structured data resides in relational databases. To access this data, you need SQL expertise. But a lot of these people simply don't have this SQL expertise. So let's take, for example, the IMDb database. So it's about the movies, actors, their relationships, like who was cast in which movie and so on. And suppose that we have a naive user, Alice, who wants to find all funny actors from this IMDb database. So Alice is looking for funny actors. And now let's see the steps Alice will have to go through for that. First, Alice has to understand the complex schema of the IMDb database, which is very hard for Alice. And the second, Alice has to learn SQL, express her intent in a SQL query like this. Again, this is very challenging for Alice, who has no programming background. There are alternative mechanisms called query by example. In these systems bypass the complexity of writing SQL and works with examples. So for funny actors, Alice might give these examples of Eddie Murphy, Robin Williams, and Jim Carrey. And the system is supposed to, ideally, detect the intent and return the list of all funny actors in the dataset. But this doesn't happen in reality. If you give these examples to a traditional query by example system, you get this, a list of all actors in the dataset. But how can we tell that Alice is likely looking for funny actors? As human, we actually see something in the examples. As human, we see the context of the example. What's the similarity in the examples? So how we can help a query intent discovery system to understand the context? So unfortunately, there is no funny attribute in the data, but there are other ways to find that. If we have a close look to the movies these actors appear in, we'll find this. A large number of these movies are comedy movies. So Jim Carrey appeared in more than 40 comedy movies, and so is true for the other two actors. This is a similarity. It's a semantic similarity in the examples. So before going to our work, I will just quickly go over the limitation of the prior art. The traditional query by example systems does not model this context. And there are methods in knowledge graphs that does not model some implicit properties, which I'll be talking in shortly. There are methods called query reverse engineering, but it requires the entire output. That fails at the first place, because if I knew the entire output, I wouldn't look for a query intent discovery system. And there are machine learning approaches and active learning based approaches, but that require either too many examples or too many user interactions. So today I'm going to talk to you about SQuID, which is an awesome acronym for Semantic Similarity Aware Query Intent Discovery. So in the next few slides, I will first talk to you about how SQuID models the semantic context, how it discovers the query, how it does so efficiently, and finally I will present some evaluation results. So the first thing is context, how SQuID represent context. So the first kind of context we consider is the basic properties. So like birth year or gender of a person is the basic property. It's directly affiliated with that person. Say male is a direct property of Jim Carrey. And the second type of context is found by aggregating over the basic properties of some affiliated entity. So Jim Carrey appeared in 40 movies that had the genre comedy. So 40 comedy movies is a derived property for Jim Carrey. So how do we encode this context in SQL? We can use selection predicates. So in our work, we use a term called filters, which is actually a combination of selection predicates. But for the purpose of this talk, you can simply assume that filters are selection predicates. So far I have highlighted to you that Alice is looking for funny actors, and I guessed it from the fact that these people appears in a large number of comedy movies. But these people are similar in many other ways. They are all male, they are all born in North America, and so on and so forth. Are all these similarities intended by Alice? How we can figure this out? The dirty truth is there is no way to be sure. So due to this uncertainty, we apply an inference mechanism called abduction. So what is abduction? So abduction is finding the most likely explanation of some observation. So in our case, our observation are the examples, and our goal is to find the most likely query given these examples. So this is in contrast with a more well-known technique called deduction, which would guarantee you that the inferred query is the one that in user's mind, but this doesn't apply in these settings. So here is our problem definition. So given the database and examples, we want to find a query such that two criteria hold. First, the example should be a part of the query output, and the query should be the one that maximizes the probability of being the intended query given the examples. So here is our abduction model, and we want to find the query posterior. That is the probability that the query is the intended one given the examples. So from the examples, we see the context, we can get the context, and just by applying some Bayes rule and some simple deductions, we come up with this equation. So we have three terms here: the query prior, which is the likelihood of a query being the intended one without seeing any examples; the semantic context prior, which is the probability of seeing a context in any random sample of examples without seeing any query; and the semantic context posterior, that is the probability of seeing a context given a particular query. So in the next few slides, I will go over these three components. First, how we model query prior. So a query is all about the filters it applies, and if we can get the filter priors, we can combine them to compute query prior. So we use three intuitions to determine filter prior. So our first intuition is domain selectivity. So it basically says if a filter is more specific, like it's getting small portion from the entire domain, then it's more likely. And the broader filters are less likely. So we have two other intuitions that mostly apply for derived filters, but I don't have time in this talk to go over this, and please refer to our paper for more details about these two other intuitions. So the second term is the semantic context prior. So how we can get the semantic context prior without seeing any of the query? So it comes from the data. So in this data, 80% of the people are from USA and 20% from Canada. So that's our prior of semantic context. That what's the likelihood that we'll observe the context USA in any random sample. It comes from the data. And the third component is the semantic context posterior. So if the query includes the filter that you specify that country should be USA, then it's trivial that you will observe that context in the examples because you are explicitly specifying it. The more interesting scenario is when the query does not contain the filter. There is no filter, but we're still seeing this context. So for only one example, the probability is simply the proportion of the data that has USA. For two examples, assuming independence, we can just multiply it and get the probability and so on and so forth. The key intuition here is that as we see more examples, it's more likely that the filter was indeed it was in the user's mind, because this cannot be just a simple coincidence. So finally, I come to the algorithm we apply. As we show in the paper, it boils down to a simple principle. So for each filter, we check if this term is higher with the filter or without the filter. If this term is higher with the filter, the algorithm picks the filter, otherwise it drops it. And with just an iteration over all the filters, the algorithm is able to construct the most likely query that maximizes the likelihood of being the intended one given the examples. So far I have talked to you about how SQuID uses context to infer query, but for a real-time query by example system, it has to be on the fly. It should happen on the fly. To make it happen, SQuID precomputes an abduction-ready database, which is an augmentation of the original database with some derived relations and semantic property statistics. And SQuID precomputes it in the offline module, and the online module consults this database to provide the user a real-time experience and computes context on the fly. So I'm done talking about how SQuID infers the query, and now we have to see how SQuID does in practice. I will see some evaluation results. So we tried to answer three questions here. So the first is how efficient SQuID is, and if it discovers the correct query intent, and how it compares to alternative techniques like query reverse engineering and machine learning. So here are the data sets we worked on, and in this talk, I will be presenting the results from the IMDb dataset, which has a complex schema of 15 relations, and we designed 16 benchmark queries. I will talk about the benchmark queries in a moment. And these benchmark queries had like up to 8 joins and 7 selections and a varying result size up to 2,000 tuples. So here is the experimental settings. So we take a benchmark query, we execute it and find some results. We mark it at the ground truth, like as if this is the tuples the user is looking for, their true intention. We sample some tuples from this result and form our example tuples. We give it to SQuID. SQuID infers a query. We execute it and we find the result SQuID produces. Now we compare this result with the ground truth in terms of precision, recall, and F-score to see how SQuID performed. So this is our results with varying examples and varying database size. And we found that SQuID's inference is linear in example size and logarithmic in database size. So it's scalable. And also the inference time was pretty reasonable. So about 5 to 10 examples, SQuID requires only few seconds to infer the right query. And here is our overall result for 16 benchmark queries. As you can see, for most of the benchmarks, the F-score rises pretty quickly. Let's focus on one particular. So it was a complex intent about finding all Indian actors who acted in at least 15 Hollywood movies. And just with 10 examples, SQuID was able to quickly detect the match the user's expectation. So I should mention that there are some cases where SQuID doesn't do as well, but we found it very rare, and this is due to the fact that the query was too complex for SQuID search space. So now I will present results comparing SQuID with query reverse engineering system, but I would like to say what the system is. So a query reverse engineering system takes the input as the entire query output, not the examples. And it reverse engineers the query and the output should exactly match the input. So an instance of a query reverse engineering system is Talos, and this is what we use for our comparison. So we found that when compared with Talos, SQuID is basically mostly better in terms of F-score, and its inference time is usually faster than Talos. However, I want to focus on this part. So this talks the quality of the query that systems are producing, and we measured the quality of the query in number of selection predicates. And note that this is in log scale. So Talos is producing way too longer queries than SQuID. So let's have a look at one particular example. So this was about finding all animation movies by Pixar. So this was the original query. This is what SQuID produced with few more extra predicates because it wasn't able to identify that these years were not truly intended, just a coincidental similarity. But this is what Talos produced. So it produced hundreds of extra predicates because it wanted to generate the exact query to match the output, and it didn't generalize and it overfit the data. So that's the problem with query reverse engineering systems. And finally, some people might see this query intent discovery system as a binary classification problem. So query is a classifier which classifies each tuple as intended or not. So in this case, we don't have any negative examples. We just have positive examples. So with that, a class of machine learning that addresses this is called positive and unlabeled learning, or PU learning in short. So we applied this, and what we found is that the PU learning approaches require about 70% of the data to match SQuID's accuracy, where SQuID does pretty well from the very beginning. Moreover, these systems do not scale as the data size keeps growing. So this is due to the fact that these generic machine learning approaches cannot model relational database management system specific assumptions, like query is the mechanism that is generating the data. So that concludes my talk. So here are a few key takeaways. So SQuID is an example-driven query intent discovery system which understands context. It exploits semantic similarity of the example. It works with very few examples. It performs well in query reverse engineering system, although it wasn't designed for that, and it outperforms learning methods. So thank you everyone for listening, and I'll take questions.